Hello, and welcome to Lecture 2 of the Principle of Relativity in Phys 1104. In this lecture, we're going to answer the central question of the unit that I posed in the last lecture, although we'll still have details that we have to work out in the remaining 2 lectures of the unit. In the last lecture, we saw that all observers in inertial frames agree about whether a system is isolated. Let's do the same thing now for energy that tells us about momentum. So here are you and Sam again on your carts, moving at constant velocity relative to the Earth, and here's Trogdor on his ruler C, also moving at some constant velocity relative to the Earth. Now, as far as you are concerned, in your own frame, you are stationary. And assuming you're not jumping up and down on your cart or doing anything like that, you're also undergoing no state change. All the same is true for Sam. And so you believe you are in a closed system. According to all your measurements, you're in a closed system, and the same goes for Sam. Well, additionally, according to your measurements, Sam and the cart Sam is on is moving at constant speed and undergoing no state change. And the same goes for Sam's measurements of you. And so you agree with Sam. According to your measurements, Sam and cart M are a closed system, and Sam agrees with you. According to Sam's measurements, you and cart E are a closed system. Finally, what about Trogdor? Well, again, Trogdor sees you moving at constant speed and undergoing no change of state, and sees Sam moving at constant speed, undergoing no change of state. So Trogdor agrees as well. So all of you agree about your systems being closed. So far, we've been looking at carts that are moving at a constant velocity, but what we really want to look at is collisions. And then we're going to hit a problem, because during the collision, the carts accelerate. And so if you and Sam are riding along on the carts, then you are accelerating, and that puts you into non-inertial reference frames. And what we just saw in the last lecture was that the law of inertia is violated in those frames. That's a problem. We really don't want to work in non-inertial frames. If you take a more advanced course, you'll learn how. There are ways to do it, but for now it's just confusing and we should avoid it. So we're going to have to make a few changes before we move on. First of all, let's take you off of the cart. And second of all, now we've got you and we've got Trogdor in a moving frame. That's all we need. So Sam, thanks for your services, but we don't need you anymore. But now I can do better than just draw pictures of you and Trogdor watching carts collide, because I've got some actual data. So here is the view of a cart collision from a camera that's fixed to the lab bench. And you can see in that video that that cart had a camera on it, like you saw in an earlier video. So here's the view from that camera moving along with that cart. And you can see in this video there's another cart over there with a camera on it. And so finally, here is the video of the collision as seen from the other moving cart. And so now we have an Earth frame and we have a moving frame on that other cart. And if we decide we need it, we also have what I'll call an internal frame from one of the carts involved in the collision. As usual, I can extract the data from that video using the video analysis software. So here are my Vx versus T curves, and we've got the Earth frame, that's you sitting on the ground measuring the position of the cart. Here's Trogdor going along on his moving ruler, and if we wanted it, we could have the point of view of one of the colliding carts relative to the other. That's Sam's point of view if Sam was still hanging around, but we've decided that's not so useful. And so here are the delta V's pulled out of the data, and you might have a look at them. And I've also measured the inertias of the carts. And so we can easily get the ratio of the inertias. Now I'm just going to comment. I could go through the whole uncertainty analysis here, but I don't think that'll be helpful in this video. That would get us into a lot of gory, horrible calculations, but I will show it in a supplemental video because I think it'll be useful to you preparing for the lab. Anyway, we can also get the ratio of the delta V's, and we see that the two ratios end up being equal as we expect, and that's confirming for us that the momentum of this system is conserved. But that is all the results out of the Earth frame, those delta V's. So what happens if we look at the delta V's in the moving frame? Well, you can see what happens because in fact the delta V's are the same, and so we get exactly the same result. But that's sort of interesting. Not only have we got the same ratio, but all the delta V's turned out to be the same. Is that a coincidence? Well, as you've probably guessed, it's no coincidence that the delta V's come out the same. So we need to work with this equation that I introduced last lecture. This is just telling us how the velocity of some object relative to a ruler A can be found if we know its velocity relative to some other ruler B and the relative velocity of the two rulers. And we're going to use that to think about, say, I could do B, but let's do A. The velocity of cart A as measured by Trogdor on ruler C, and applying this equation, it's going to be the relative velocity of Trogdor's ruler relative to the Earth plus the velocity of cart A as measured in the Earth frame. And I can rewrite that both for the final and the initial. And you might be wondering why VCE has no F or I on it, but that's constant, right? The ruler C is moving at a constant velocity relative to the Earth, and so VCE doesn't change, and I don't need an initial or final subscript on it. And just note that VCE would be nothing more than negative VC. So as long as we know this velocity of this ruler, we know that. Although it's going to turn out to be totally irrelevant. You'll see we don't even need to know this. So now let's just work with the definition of a delta V, right? So this is the delta V as measured by Trogdor. And I've circled these to show that I'm going to substitute this part in for the final and this part in for the initial, and so I get an expression that looks like this. And look at what happens. The VCEs cancel out. They're gone. That's why I said it doesn't matter what VCE is. It's guaranteed to just cancel right out. And so we're left with this expression. But look at what that is. That is the final velocity of cart A as measured in the Earth frame minus the initial velocity of cart A as measured in the Earth frame. So that is just the delta V as measured in the Earth frame. And so we've seen that the two delta V's came out exactly the same because these VCEs cancel. And this will always work for any pair of frames, so we can say the change of an object's velocity is the same in all inertial reference frames. So now we have our answer to part of our original question. Because you and Trogdor agree on the delta V's, and you also most definitely agree on the inertias, every observer agrees on those, that means that you agree on the change in the system's momentum, and in fact that the change in a system's momentum is the same according to observers in all inertial reference frames, which means that if one observer sees an object conserving its momentum, all other observers in inertial reference frames will agree. Does this also work for energy? Let's go back to the data and see, because if all observers also measure the same change in kinetic energy, that would be awfully convenient, wouldn't it? So you can verify, just reading the velocities off of the graph, that these, or at least roughly, you can verify that these are the kinetic energies as measured from the Earth frame for cart A. And so there is the change in kinetic energy for cart A. And again, you can verify, reading values off of the graphs, at least roughly, that those are the kinetic energies as measured from frame C, from the moving cart. And so there's our kinetic energy as measured from the moving cart. And wait a second, those don't match. So apparently different observers do not measure the same change in kinetic energy for an object. Well, that's kind of disappointing, isn't it? Well, all is not lost. Instead of looking at the kinetic energy of the individual carts, let's look at the kinetic energy of the system. So for this one, and again, you can verify this just by running the numbers as well as you can read them off the graph, The kinetic energy of the system is initially 0.4 joules and finally 0.4 joules, where I'm going to say everything in that gray box is things calculated from the Earth frame, so I don't get into more subscripts. Well, look, the kinetic energy of the system didn't change, and so we can conclude that this is an elastic collision, as seen from the Earth frame. Does it work out that way in the moving frame? Well, again, you can pull the numbers out of the graph and you can see that the kinetic energy of the system is 0.14 joules both before and after the collision. And so again, in the moving frame, we also conclude that the collision is elastic. So even though the change in kinetic energies of the individual objects are different depending on which reference frame we calculate them in, it turns out that we conclude that this collision is elastic, no matter which frame we use. In fact, we kind of already knew that all inertial observers will agree on whether a collision is elastic, because we know from the last lecture that all inertial observers measure the same relative speed between objects. And that was actually our definition of an elastic collision, that the relative speed doesn't change. And so the inertial observers are certainly going to agree on that. And just realize why that is. It's actually the same argument we made before, that the relative velocity is formed by just that subtraction of the two velocities. And when you transform that from one frame to another, so here we are transforming from the Earth frame to the moving frame C, then because of this subtraction, the two VCEs that end up in here cancel out. Anyway, we derived kinetic energy conservation from the relative speed not changing, and since inertial observers agree on the relative speeds, they've got to then agree on the kinetic energy being conserved in an elastic collision. Still, it's concerning that different observers don't measure the same changes in kinetic energy for the individual objects. What does that mean for inelastic collisions, where now the relative speed changes? Are two different observers going to agree on the change in the system's kinetic energy in this case? That's worrying, given that they don't measure the same changes in kinetic energy for each object. Well, in fact, we can argue they must, because they have to agree on the change in internal energy. Why do they have to agree? Think of what that change in internal energy means. It's things like the deformation of the system. And both observers, if you see a certain deformation in an object, any other observer is going to agree with you about what that deformation is. And so you have to agree on the change of internal energy because it's a result of those states of the change of the system. And since the kinetic energy changes only by that kinetic energy turning into internal energy, if the system is closed, we can see that the different inertial observers are going to agree on the change in the system's kinetic energy. If you don't like that explanation, if it seems a little hand-wavy, don't worry, I'll give you a more mathematically rigorous derivation of this in another lecture to come. Summing up, we've seen that for inertial frames, momentum conservation is independent of the reference frame. And so is energy conservation. In other words, all observers in inertial frames agree that these two laws are true. And so this is a symmetry. It might not be obvious to you that this is a symmetry, but it is the symmetry where we see that these laws are invariant under a transformation from one coordinate frame to a different frame moving at a different velocity. And here is the principle of relativity. The laws of the universe are the same in all inertial reference frames. One of the consequences of that is that inertial frames are indistinguishable. An experiment carried out in one frame can't tell you how fast that frame is moving relative to any other. And so we don't prefer any frame. I've tended to sort of prefer the Earth frame, but there is no reason to prefer any frame. And you've seen this, that no experiment tells you anything about the velocity of your frame. This flight attendant can pour that coffee in exactly the same way they would standing on the ground, even though the plane they're in is probably going over 250 meters per second.